Good day, this is Dusty again, and today we're going to talk a little bit about conic sections. This is just a quick overview of conic sections, trying to give you a feel for what's going on with them to set you up for success in a section, a later section that's multivariable, that's in 3 dimensions. So this is a crash course in the 2-dimensional version of conic sections. Just a few questions for you in the homework here. Again, all just to give you a taste for what's coming up. So conic sections. So conic sections are the curves we get when we make a straight cut in a cone. As shown below, there are 4 interesting conic sections: circles, ellipses, parabolas, and hyperbolas. There's also a couple of other conic sections that are, maybe you could say, less interesting. And I'd also like to note that the circle is just a special case of the ellipse. Let's look at a manipulate so we can get a better sense for what these conic sections look like in 3D. So as I indicated below, conic section is what happens when you start with a cone, in this case, almost like a cone on top of a cone, and we make a straight cut through it, like a big old slice. In this case, notice the shape that's being made is an ellipse, and as we change the tilt, the ellipse kind of morphs into a circle. We keep changing that tilt, going all the way up. Here, our shape of the cut is a parabola, and we keep changing that tilt, and eventually we're going to get a hyperbola. So let's look at each one in turn. So a circle is what happens when you cut horizontally. An ellipse is what happens when you cut at an angle, but not too steep an angle. We want to make sure that we are cutting right through that ellipse. You can get parabolas pointing to the left. If we kind of cut our plane this way, notice we miss the cone over here on the lower cone, but we're just hitting the upper cone. Or we could cut, get a parabola on the other side if we sliced and from left to right. Hyperbola will be the result if we cut straight up and down. Of course, you can get just a point if we grab just a tip, like where the 2 cones come together. So the point would be just the point where the plane and the cones meet. You get a single line. You happen to very cleverly just line up with the very edge of the 2 cones. And we could even get a pair of lines if we slice straight down and manage to get kind of both edges of the cones. So once again, the conic sections are all of these different types of shapes that we're talking about here. But the interesting ones are really the circle, the ellipse, the parabola, and the hyperbola, remembering again that the circle is just a special case of the ellipse. Example 1. Identify the type of conic section whose equation is given. A, x squared equals y squared plus 1. So we could start by moving it into our standard form. So we have x squared minus y squared minus 1 equals 0. Here's our 2 terms that have the squares in them. And notice they have opposite sign. And so this is a hyperbola. Because of the opposite sign. All right. In B, we have y squared minus 8y equals 6x minus 16. Again, we could put it in standard form. So we have y squared minus 8y minus 6x plus 16 equals 0. I'm not going to worry about putting the x's first in this case. I notice that there's only one term with a square in it, And so this must be a parabola. Because there's just the one term with the square. All right, in C, we'll again put it in standard form. So we have the x squared plus 4x plus y squared minus 10 equals 0. We have the two squares. They have, notice, the same sign, plus and plus. And we also notice that there is a 4 in front of the first term, but a coefficient of 1 in front of the y term. So this tells us that we have either an ellipse or a circle. Or circle. But since we have the different coefficients in front of the x squared and the y squared, we know this is an ellipse. Historical note. The history of conic sections begins around 300 BC and continued for nearly 2,000 years. For most of this time, conics lived entirely within the realm of geometry. It was about pictures. It was about diagrams, straight edges, angles, and constructions. But in the 1600s, Descartes and Fermat found a way of representing geometry algebraically. A taste of this analytic geometry is in this section. The first of the conic sections we're going to discuss is the parabola, and here we're talking about it with a geometric definition. So a parabola is the set of points in the plane an equidistance from a fixed point F. So here's our fixed point F, which is called the focus, and a fixed line L, which is called the directrix. Fixed line L. And so we notice that the distance from the point, the focus, to the curve is the same as the distance from the curve to the directrix. Or again, from the focus to the curve, the same as the curve to the directrix. Okay. The vertex of the parabola is halfway between the focus and the directrix. This is our old friend, same vertex as before. Okay. And it's also, there's also an axis of symmetry, and that's the line that runs through the focus that's perpendicular to the directrix. So our axis of symmetry, that's this line, goes through the middle. So note, pay attention to explanations that are from geometry versus analytic geometry. So here we're describing things in terms of lengths and things that you could draw with a ruler and lines. There's no y equals x squared anywhere in sight here, even though the picture itself should be pretty familiar to you. So let's look at this parabola in an animation. So notice that we can change our shape, but in each one of these cases, we have that the distance from the focal point to the curve is the same as the distance from the curve to this line, the directrix. We could change to a different point. We're over here, but again, the distance from the focus to the point is the same as the distance from the point to the directrix. This is going to be true whether we have a smiley parabola or a frowny parabola or a parabola opening to the right or a parabola opening to the left. All of these are parabolas. These are kind of our standard shapes. And they've been described kind of since ancient times in this method where we're talking about lengths being the same from this focal point to the directrix line. In this top box, we look at a parabola with a vertical axis. That would be this vertical axis here. And so this would be the graph of the equation x squared equals 4py. That's where our y equals x squared is coming from in our world. It's a parabola with the following properties. It has a vertex at 0, 0, a focus at 0p, and a directrix at y equals negative p. So you can see the smiley version here. You can see the frowny version. Smiley versions where p is greater than 0, the frowny versions where p is less than 0. Parabolas can also open to the right or to the left. So the parabola with the horizontal axis is as follows. The graph of the equation y squared equals 4px is a parabola with the following properties. It too has a vertex at 0, 0, but now the focus is at p0 and the directrix is at x equals negative p. The parabola that opens to the right takes place when you have p bigger than 0, and the parabola where that opens to the left is where p is less than 0. We can use the coordinates of the focus to estimate the width of a parabola when sketching the graph. The line segment that runs through the focus perpendicular to the axis with endpoints on the parabola is called the latus rectum, and its length is the focal diameter of the parabola. This length is the magnitude of 4p. So let's see if we can understand what's going on here. So it says the line segment that runs through the focus perpendicular to the axis. So here's your focus, and we want to go perpendicular to that axis right there. Perpendicular to the axis with endpoints on the parabola. So we want to go all the way from end all the way to end. This is called the latus rectum, and its length is the focal diameter of the parabola. This length is the magnitude of 4p. One of the things that you might notice here when it talks about focal diameter is that might give you a hint or a reminder of things like focal length. Okay, so it reminds us of this. And indeed, the parabola is the shape of many of the lenses that appear in optics, from telescopes to cameras, probably even to glasses. So there's this, you call these special characteristics in a parabolic lens or a parabolic mirror. Ellipses, a geometric definition. An ellipse is the set of all points in the plane such that the sum of their distances from two fixed points, which is called the foci, is constant. So here's a picture of the ellipse. And what I want to point out is that the length of the string is the dotted line in the picture. The total length of the string, starting at F1, going to P, and then back to F2, remains constant. So it's moving around. So you can actually make an ellipse pretty easily by fixing 2 points, like putting 2 tacks in a board, making a string, and then letting that string kind of trace out your ellipse. That's your geometric version. Let's look at that constant sum. We add the two together, notice that you're always getting the same length. You've got a circle going from F1 out to this big purple circle. If we make it a kind of longer ellipse, same thing is true. If we make it a square ellipse, maybe make them both big. If both the width and the height are the same, then it's a circle. And notice in the circle, it's like you start at center, then you go there, back to the ellipse and then back again. It's kind of a boring. Here, maybe you can see it with a near circle. You can see that the two lengths are always about the same, almost just about the radius, but not quite. So there's a picture of the ellipse. So an ellipse with the center at the origin. The graph of each of the following equations is an ellipse with center at the origin and having the given properties. So if we have the equation x squared over a squared plus y squared over b squared equals 1, and a is bigger than b, bigger than 0, then you're going to have vertices at plus or minus a 0. So that would be these 2 points here. And you have a major axis that has length 2. So the long diameter, if you will, the major axis is length 2a. The minor axis here, the short diameter, if you will, the minor axis has length 2b. And the foci are at plus or minus c comma 0. So these foci, these are these 2 points, like the 2 points that the string would attach, where the string would attach. If we looked at x squared over b squared plus y squared over a squared equals 1, where a is bigger than b is equal to 0, now you have a tall and skinny ellipse. It's got a vertical length of 2a, that is, your major axis is 2a. It's got a minor axis or a horizontal length of 2b. And now your foci, or your fixed points, if you will, are at 0 comma plus or minus c. Fixed points are there. In the standard equation for an ellipse, a squared is the larger denominator and b squared is the smaller. To find c squared, subtract the smaller denominator from the larger one. So if we want to find the vertices and foci of the ellipse, x squared plus 3y squared plus 2x minus 12y plus 10 equals 0. And then now we want to sketch the graph. This is example 2. So to do this, I'm going to start by separating out the x stuff and the y stuff and completing the square. So if we focus on our x stuff to begin with, so I have x squared plus 2x, and I'm going to leave a little space, plus 3y squared minus 12y. Then I'm going to leave a little space, maybe plus 10 equals 0. So we notice that we can complete the square on the, so here's our x stuff, and here's our y stuff. So I can complete the square on the x stuff by adding in a plus 1. If I add 1 on the left, then I've got to add 1 on the right. And so this gives me x plus 1 quantity squared plus, I noticed that there's a common factor of 3 between the 3y squared and the minus 12y. So I can factor that out. And I'm left with y squared minus 4y. Again, I leave a little blank. Plus 10 equals 1. To complete the square for the y, it looks like I need to take the -4, divide by 2, -2, and square it. So I could add 4 to both sides. And this gives me x plus 1 quantity squared plus 3 y minus 2 quantity squared. And then if I moved everything to the other side, I would have minus 5. I feel like there's a typo in this question because I think I would like to have a positive number on the right side for an ellipse. Because how can I have a square positive number plus another square, another positive number equal a negative number? So I think there's a typo in the way this is written. So I'm going to just make a little executive choice here, and I'm going to change the question. Instead of being a plus 10, I'm going to make it a minus 20. So now if I come back through here and change it, it will be minus 20, minus 20, and now we'll have plus 25. My apologies for the confusion there. Whew. So we recognize that the coefficients in the front, the 1 and the 3, are different. We also notice that we have a plus in the middle. So we have two squares, we're adding them together, but different coefficients. So this tells me that I have an ellipse. And should be pretty clear that our ellipse is centered at the origin. Or sorry, centered at -1, 2. -1, 2. The -1 is coming here from the +1, and the 2 is coming from the -2. Because remember, there's that minus sign that's built into the formula. We could write minus or +1 as -1. So we know where our ellipse is centered. Now we've got to find the vertices of our ellipse. So to find the vertices of our ellipse, what we could do is we could put ourselves onto either the major axis or the minor axis and see what happens. So my key values are this x equals -1 and the y equals 2. So if I let x equal -1, right, then this first set of parentheses, so I'd have -1 minus -1, or -1 plus 1, or 0. So I'm going to get 0 for this first term. And so I'm going to be left with 3 times y minus 2, quantity squared, equals 25. Y minus 2 is going to equal plus or minus the square root of 25 over 3. Or y is going to equal 2 plus or minus 5 over root 3. So that's going to be one of my sets of vertices. And then if we let y equal 2, then again, the second set of parentheses, the y minus 2 quantity squared, would become 0. And so we would just be left with that first bit. And so we are left with just x plus 1 squared equals 25, or x plus 1 equals plus or minus the square root of 25, or plus or minus 5, or x equals -1 plus or minus 5. So let's see if we can figure out how to graph this ellipse. We have our axes, x and y. We know we're centered at -1 and 2. Here's our center. And then we know when y equals 2, maybe I'll do the easier numbers first. So when y equals 2, our x's are going to be -1 plus or minus 5. That would be, pardon me, -1 plus 5, which would be 4. So I've got -1, 0, 1, 2, 3, 4. I've got a point here, and I've got -1 minus 5, so -1, -2, -3, -4, -5, -6, or there at -6. Okay. And then if we look at, so these are our points that are coming out from the y equals 2. We look at x equals -1, then the points that are going to come out are y equals 2 plus or minus 5 over root 3. So that's going to be, let's see if I have a calculator around here. 5 divided by square root of 3, 2.8 or 2.9. So it's going to be 2 plus or minus 2.9. So we would start at the 2 and we would go up 1, 2, 2.9. So here's 2 plus 5 over root 3. And then we would start at the 2 and we would go down 1, 2. So here would be 2 minus 5 over root 3. Those would be my other vertices. And now we should be able to connect the dots to make the ellipse. What color to use? How about blue? So I know I'm going to be vertical slopes, the 2 yellow points, horizontal slopes at the 2 blue points, and then I got to make my curve wrap around. Okay. So here's a picture of my ellipse. The only question that remains, I believe, is finding the foci of the ellipse. So we found the vertices, but we also have to find the foci. And so we are in the case of the like the horizontal shaped ellipse. And in this case, we remember that our foci are at plus or minus c comma 0, where c squared equals a squared minus b squared. Okay. In our case, the a is the, oh my gosh, what's our a and our b? I never put this in standard form. So to put this fully in standard form, I would have to divide through, so I have fractions. So pardon me for having to go back. So it's like I'd be dividing through by 3 in all these cases. Oh, sorry, my bad. I'd be dividing through by 25. Be dividing by 25. And we'd notice that 3 over 25 would be the same thing as putting a 25 over 3 in the denominator here. So in this case, my a is coming from that 25. And so a squared is 25. And my b squared is 25 over 3. So let's get my colors right. Here's 25. Here's 25 over 3 for b squared. And so our c squared in this case is going to be 50 over 3. And so our foci are going to be and this is a little bit interesting. These are centered at the origin, so I got to be a little bit careful. So so at first glance, it looks like our foci are going to be at plus or minus square root 50 over 3, comma 0. But we have to take into account the center of this particular ellipse not being at the origin. So counting for the shift, the foci are going to be at the center that we were given, -1 and 2, and it's going to be -1 plus or minus that square root of 50 over 3. So let's see if I can make sure the colors are coming through here. So here's the -50 over 3, and here's our center coming from the center of the ellipse. So a few complications in that particular question, because the ellipse isn't centered at the origin and we had a typo, but nevertheless, not too bad. The last conic section that we wanted to discuss is the hyperbola. We want to give a geometric definition. So a hyperbola is the set of all points in the plane such that the difference of their distances from the two fixed points, which are called the foci, is constant. The segment joining the two vertices is the transverse axis of the hyperbola. The asymptotes are the lines that the hyperbola approaches for large values of x and y. So this geometric definition for the ellipse is a bit of a challenge, but nevertheless not too bad. So let's see if we can see it in the picture. So what we're saying is that the distance, we look at the distance from your focus out to a point on the ellipse, or on the hyperbola, I'm sorry. And then you keep going from that same point all the way back to the other focus. And then we're going to look at the difference between the two lengths. So it looks like the difference between the two lengths, we kind of like came through here. It looks like the difference is about maybe looks like this long. And that length is the same as this length here. Let's do that again. So if we chose a different point, let's see if I can choose a different point. So maybe we've got a difference point here, different color. So if we look at the two lengths, so if here's focus to the ellipse, or sorry, I keep saying ellipse, focus to the hyperbola, and then hyperbola back to the other focus. And we got to ask ourselves, what's the difference in length? So let's see, so we kind of right around it. The difference in length is about this far right here. And again, that's the same as the distance between the two vertices. So that's where our definition for the hyperbola is coming from. So we can have horizontal hyperbolas, we can have vertical hyperbolas. They can be wider or narrower. Okay. You can also adjust how high they are or low they are, as in kind of where are those focal points. And then you'll notice that there are asymptotes that the hyperbolas are approaching. If you ever want to sketch a hyperbola, it's not too difficult to do so. Basically, you find the 2 points where the hyperbola actually kind of has its vertices, and then you can use those to sketch the box, which gives you the asymptotes. And so you've got your asymptotes and you know your known point. And so you kind of start at your known point and then approach the asymptote. So it takes a little bit of practice, but it's not too difficult. So again, the hyperbola with the center at the origin. Graph of each of the following equations is a hyperbola with center at the origin and having the given properties. So first, we have x squared over y squared minus y squared over b squared equals 1. So notice the x's are positive, the y's are negative. So you're going to have vertices at x equals plus or minus a and 0. It's got a nice horizontal length. The asymptotes are at plus or minus b over a x. The foci are at plus or minus a comma 0. And our graph, notice those foci are at plus or minus, I think plus or minus c comma 0. I think I said a. So that's these points. And the vertices are plus or minus a. That's these points. Okay. And so you know that it's going to open to the right or to the left. You can draw your box through the A's. Notice the B's are going to give you the vertical part of the box. And since you've got those given points, the asymptotes, again, not going to be too difficult to sketch. For the other version, for y squared over a squared minus x squared over b squared equals 1. Okay, now the vertices are at 0 plus or minus a. So here, your vertices are up and down instead of side to side. You're going to have a vertical length of 2a. Again, you have asymptotes, but here they're at plus or minus a over bx. Your foci are at 0 comma plus or minus c. And we know that our box will have kind of top and bottom at plus or minus a and side to side at plus or minus b. Sketch your asymptotes, start at your fixed points, and approach the asymptotes. You get your nice, pretty sketch. So just wrapping this up, how to sketch a hyperbola centered at the origin. Sketch that central box. This is the rectangle centered at the origin with sides parallel to the axes. It crosses on axes at plus or minus a, and the other at plus minus b. We sketch the asymptotes. These are the lines obtained by extending the diagonals of the central box. You plot those vertices. These are the 2 x-intercepts or the 2 y-intercepts. And finally, sketch the hyperbola. Start at a vertex and sketch a branch of the hyperbola approaching the asymptote. Sketch the other branch in the same way. So given that people worked on conic sections for a couple 1,000 years, I dare say there's quite a bit more to it than we have in this one section. But that should be enough to give you a basic feel for parabolas, ellipses, and hyperbolas. And in the next section, in a later section, you will see us looking at quadric surfaces, and it kind of helps to have a feel for what these various shapes are before we move to those quadric surfaces, which live in 3 dimensions. So thanks very much. I hope you enjoyed this lesson on conic sections.